Hello, Math 220 students. This is a video that is intended to help us round out case study 2b. You may find that it goes a little faster than a lecture. If you feel that's the case, then feel free to pause the video along the way. But you recall in case study 2b, we're saying something about all students taking intro stats, in particular, the average GPA of all students taking intro stats. And this question of interest was whether or not the average was different than 2.889. 2.889, you recall, was the overall university average GPA. And so we're comparing the average GPA of all students taking intro stat to the overall GPA average for all university students. Okay, so we went through within this case study and we talked about how this particular theorem would not apply because our data is not normally distributed. The GPA data, you recall, appears to be left skewed, and so we cannot use the regular t-test that we developed in case 2a. So we went through here through a discussion that went a couple of pages long through this idea of the central limit theorem that basically said if we take a random sample and our sample is large enough, then the distribution of x bar is approximately normal. Okay, and we saw the central limit theorem kind of come to life in the simulation that's highlighted by these pictures, that when the sample size is 4, 10, up to 50, when we're sampling from a right skewed distribution, you see the distribution of x bar approaches normality. All right, and we saw that for two other populations as well. So that's a bit of a review. In particular, here is the central limit theorem in lay terms. Here it is in more formal terms. But the big idea is that x bar is approximately normal if we have a random sample from any population and that random sample is sufficiently large enough. For us, the large enough value, we'll just set it at 30 or more. There can be some discussion on if that's high enough. For some underlying populations, that's really more than what you need. For some other underlying populations, it's not quite enough. But for what we'll run into, and just to kind of draw a line in the sand, we're going to go with 30 or more, allows us to invoke or to use the central limit theorem. Okay, so now back to the lecture here, continuing where we left off. We have, remember, we are wanting to test this hypothesis. Is mu equal to 2.889 versus not equal to 2.889. So we need to talk about our test statistic and sampling distribution. We will use the CLT because our sample size is large. So by the CLT, we can state that, hey, our statistic x bar minus mu over x bar minus mu over sigma over root n is approximately standard normal. All right, if x bar is approximately normal and we standardize x bar, then x bar is approximately standard normal. All right, and this is even the case with the non-normal population of GPAs. Okay, and that's the power of the central limit theorem. It says that you can sample from whatever population that you're interested in, provided your sample size is large enough. X bar is approximately normal. All right, so even that's a powerful result for us. Now it turns out, and we won't go into a lot of detail here in this class, that when n is large, S is sufficiently close to sigma. Now, why am I talking about this? Well, this test statistic is not useful for us because we don't know sigma, the standard deviation of the population. So it makes sense to replace it with S. And if we replace it with S, when n is large, it turns out S is pretty close to sigma, and in turn, this ratio with S in the denominator, I'm going to call it Z also, also follows an approximate standard normal distribution. Now, because of that, I mean, things are approximated. The p-value that results from this null distribution will be approximate, but this approximation will be very good since the sample size is large. Okay, the sample size is 90. Now, moving on here to the next page, the concluding decision, we have our test statistic in mind, and we just need to compute that thing. Okay, so our observed test statistic, I'm going to put Z with a subscript of OBS to tell us it's an observed test statistic, is going to be X bar minus mu over S over root N. Okay, X bar, you recall, is 2.733. That was the average GPA from the 90 GPAs in our sample, minus mu. Well, what do we plug in for mu? Well, you plug in the value of mu under the null hypothesis. Look back on the previous page, or the first page of notes here. The value of mu under the null is 2.889. Okay? We are assuming the null hypothesis is true in the computation of this test statistic. S was computed to be 0.762, and of course N here is 90. So S over root 90. And if you do this computation, you should get negative 1.94. All right. So that's our observed test statistic. Now, how likely is this, assuming the null hypothesis is true? Well, getting at that question, we need to compute the p-value to get at that question. So the p-value here is, now you remember we talked about it in a previous example, that with a two-tail test you multiply the corresponding probability by 2. We're going to multiply 2 times the probability that Z is less than or equal to negative 1.94. Alright, this is again because of the two-tail test here. So we got 2 times, this is going to be an area. Now we're dealing with the Z distribution, not the T, although if we look at the T we'd get something pretty close, because you recall the T is close to the Z distribution when N is large. Alright, so, but anyway, I've got negative 1.94, and I need the area under the curve to the left of that. If you look on table N, you will see that that value is 0.0262. Okay, so this is from table N, which we have used in this class quite a bit. So the p-value is 0.0524, or really that's the approximate p-value. All right, but we can feel pretty good about that being close to the actual p-value because our sample size is so large. So to recap what we've done in case, this is not case 2a, right? This is case 2b. To recap case 2b, the parameter of interest was the population mean GPA for all students enrolled in intro stats. And the hypotheses were the null mu is equal to 2.889, mu is not equal to 2.889. You recall this alternative was driven by the claim that we wanted to test. That is that the average GPA among students taking intro stats is different than the average GPA of all students at the university. We talked about our test statistic. We developed this test statistic, and this test statistic is viable because our sample size is large, and that when we go to the next step, because our sample size is large, the distribution of this test statistic is an approximate standard normal. And of course the central limit theorem, the CLT, is driving that result. The observed test statistic was negative 1.94. The resulting p-value, two-tailed p-value, 0.052. All right, so what do we do here? What's our decision? Well, up front, we never came up with an alpha. And if we wanted to develop a type 1 and type 2 error analyses, we could have. But this is right on the line of where you might reject and fail to reject. Pretty close. But overall, the decision would go something like this. We would reject H naught and accept HA if our alpha values, the significance levels, maybe I should say significance levels, the alpha values were much greater than 0.052. Okay, so if we were more fearful of making a type 2 error and we set alpha to be closer to 10%, then we would reject H naught and accept HA. But on the other hand, if we were more fearful of making a type 1 error, then we might set alpha at 0.01, and so we would fail to reject H naught in that case. So the interpretation then is kind of a sliding interpretation. For moderate to large significance levels, we have sufficient statistical evidence to support the notion that the average GPA for all students enrolled in intro stats at the university is different than the average GPA across the entire university. All right, so that's our takeaway for the case study. So it's kind of closing the loop, so to speak, to get back to the original question that drove the case study. Okay, so you might guess what's coming up next here. We have evidence that mu, the population mean, is different than 2.889. Where might the value of mu be? Let's do an estimate for it. As it is now, our best point estimate is the sample mean, which was 2.733. But let's give a more sure estimate. Let's give a confidence interval for the population mean mu, where we can give a range of values and a confidence level for our particular range of values. Now, in terms of giving the formula, we're not going to develop it, but if you, I'll just present it here. In summary, for large samples, random samples, n is bigger than or equal to 30, from any population, an approximate 1 minus alpha 100% confidence interval for mu is given by this expression here. Now, when you look at this looks a lot like what we had in case 2a, and it's very similar. The only thing that's different is we've replaced z with t, and that's because our test statistic that we began with followed a standard normal distribution for large n, and that's why that's a z percentile there. Now, that said, if you actually put a t percentile in place of this z, you're going to see you get something very close to it, because the t percentiles are very close to the z percentiles for large sample sizes. So this is our confidence interval for mu when the sample sizes are large, and the central limit theorem basically is the behind the scenes tool that's allowing us to make this sort of statement. The derivation that we alluded to in case study 2a for that confidence interval is very similar in nature to the derivation for this confidence interval formula. All right, you just have z percentiles instead of t percentiles. Okay, so but let's look at here our confidence interval for mu in case study 2a. A 95% confidence interval, and we're going to use this formula, right? X bar plus or minus z percentile times s over root n. Okay, well, so from our sample, recall the sample mean is 2.733 plus or minus, and we got to figure out what is our z value. Well, we got a 95% confidence interval, so our confidence level is 0.95, So the alpha then is 0.05. So z sub alpha over 2, or z sub 0.05 over 2, z sub 0.025 is, what is that? If you want to draw a picture here that may be helpful, it's the value of z such that the area under the curve to the right of that value is 0.025. Okay? This is on the standard normal distribution now, not just the t. That turns out to be, if you look in table N, that value turns out to be 1.96. Back to the picture though, the area under the curve to the right of this is 0.025. The area under the curve to the left of it must then be 0.975. So you look for a left area of 0.975 and check its associated z-score, and if you look at table N, you'll see that it's 1.96. Okay, so I've got my z percentile, 1.96, times s. S here, 0.762 divided by the square root of 90. These three things, x bar, s, and n, are all determined by the sample. And then this is determined by the confidence level. Okay, so we take our point estimate, 2.733 plus or minus 1.96. And then if you take that product there, what do we get? And I'm looking for a calculator here. So we'll take 0.762 divided by the square root of 90. And if you do that, you get 0.08032. Okay, remember some of the language we've used for confidence intervals is this: if this is our point estimate plus or minus a percentile times the standard error of the point estimate. Our confidence intervals, they all have that form. All right, all have that form. So if I ask you, does the confidence interval contain the point estimate, you would say, yeah, it's right in the middle of it. And we would want to be aware of that. Doing the arithmetic here, 1.96 times 0.08032 is 0.157. And then if we subtract that from 2.733, we get 2.576. Add that to 2.733, we get 2.890. Okay, so that's our resulting confidence interval, a 95% confidence interval. And if you look at it, you recall what was H naught and HA for our hypothesis test. Mu is 2.889 versus mu is not equal to 2.889. So this value of mu under the null is just barely inside this interval, just barely under the right limit. And so according to this interval, is 2.889 a plausible value of mu? Well, yeah, it is, but just barely. And so you could imagine if we adjusted our confidence level, if we made it a little bit smaller, it would make the interval a little tighter and would not contain 2.889. All right. But as it is here, we would, using this confidence interval to make a decision about this hypothesis test, we would fail to reject the null hypothesis. Okay. But back to the interval, the interpretation here of the interval would go as follows. We are 95% confident that the average GPA of all students taking intro stat, that average is between 2.576 and 2.890. Okay, So if somebody said, hey, do you think that average is as low as 2.4, we would say, no, that's not a plausible value. These are the plausible values in here. So we would reject that idea. Or somebody said, do you think the average GPA for all students in intro stats is 3.2, we would also reject that idea based on this interval. Okay, so there's the interpretation. Moving along here, we're going to come to an example. Now, in this example here, on the next page, take a moment to read it. You may want to hit the pause button, but I'll just kind of go through it. Bob Nail is the owner of Nail's Texaco Gastown, and a customer claims that the average amount of gas pumped from a sale at Gastown is greater than 12 gallons. To test this claim, Bob selects a random sample of 50 sales and finds the sample mean number of gallons sold is 13.8, and the sample standard deviation is 3.5. Can we conclude at the 1% significance level that the customer's claim is correct? In order to test this claim, let's identify and execute the following components of the appropriate hypothesis test. So there's the usual pieces that we want in steps 1 through 8, and then also in step 9, let's compute and interpret a confidence interval. Okay, so I have worked this out, and I'm going to kind of reveal the steps to you one at a time. You may want to make use of the pause button on your computer or whatever you're watching this with as you need to. But if you think about the population here, it's all gas sales at Nail's Texaco Gastown. That's what we want to say something about. That's what the customer's making a claim about. And the information that we have is only on 50 sales. And so he's interested in saying something about all gas sales across some reasonable time period. That's our population. And the thing that he wants to say something about within the population is this parameter, the average amount. So it's a population mean, the average amount of gas pumped for all gas sales at Nail's. All right. And then in step 3, what do the hypotheses look like? Well, the claim we want to test goes in the alternative. All right, what was the claim? Customer claimed that the average amount of gas pumped is greater than 12 gallons. And so can we conclude that the customer's claim is correct? So we're going to put that in the alternative hypothesis here. Identify that first, mu is greater than 12. And so the null then, you could write it two ways. If you wrote that mu is equal to 12, that would be fine. Or if you wrote that mu is less than or equal to 12, that would be okay too. So that's our hypotheses. Just a comment here. Notice I don't have X bar in my hypotheses. I would never write a statistic in the hypotheses. I would never have anything like X bar or P hat or S. Okay, because I know those quantities from the sample. We're doing a hypothesis test on an unknown parameter. All right. Step 4, our observed or our test statistic is going to be a z-test statistic. We can apply this test statistic because our sample size is large. All right, we've got 50 data points from this sample. There was 50 sales that were observed. And so we're going to apply this test statistic and see in step 5 that the distribution is approximately normal. If we go through and observe our test statistic for our given data, x bar minus mu over s over root n. X bar, you recall, is 13.8. Mu is 12. S is 3.5, and n is 50. So the observed value is 3.6. So the null distribution here, just to be clear, we need our test statistic, but we want to know how it's distributed so we can talk about, in some sense, the likelihood of seeing our particular statistic, assuming the null hypothesis is true. This is approximately standard normal under the null hypothesis. That is, assuming H naught is true, we've plugged in 12 under the null, okay, for mu. Because of that, we've assumed H naught is true, and this thing is an approximate standard normal distribution. Now, this is true by the CLT. It's driving that result. It's a mathematical result that's helping us make that sort of statement. So that's our null distribution. We will use that to compute our p-value. And so here's our p-value set up. Now, this is a left tail test. No, I'm sorry, it's a right tail test. Right tail test. So our p-value is going to be the chance of seeing something as extreme or more extreme than what our sample yielded. Our sample yielded a test statistic of 3.64. The chance of seeing something more extreme than that or as extreme is the probability that z is bigger than or equal to 3.64. All right, so let's set up a picture for that. The picture for that is over here. Here's 3.64. That's my observed test statistic. I want the area under the curve to the right. That's going to be my p-value. Now I've got several things here. When I look at table n, so let's see here. I'll get table n, put it on the screen. The z-value, the largest z-value we have in table n is 3.09, and the corresponding left area with that is 0.990. So what do we do with that? Well, we know that, hey, 3.09 has a left area of 0.990. That means it has a right area of 0.001. Now that 0.001 is the area here between 3.09 and 3.64 plus the area to the right of 3.64. So because of that, this right tail area, this p-value, has got to be less than 0.001. So my p-value is less than 0.001. All right. So with that kind of p-value, it's a small p-value. It's less than the alpha we chose at 0.01. Because of that, we reject H naught and accept the alternative hypothesis. That's our decision. Kind of a mechanical thing. What does this mean in the context of the problem? That we have sufficient statistical evidence to conclude that the customer's claim is true. In other words, that the average amount of gas pumped for all sales at Nails is greater than 12 gallons. Okay, so maybe this customer or maybe Nail himself might use this information in the way he forms his gas pumps or the way he sets up his system to dispense gas. So this is the hypothesis step, hypothesis test, steps 1 through 8. Moving on to step 9, the confidence interval. Let's see if I can get the page for that here. The confidence interval for us. All right, 99% confidence interval for mu. Again, we're using this formula, x bar plus or minus z times s over root n. Well, what do we need? We need our sample mean, we need our sample standard deviation, and our sample size. The sample mean, if you go back and look at the problem, you'll see the sample mean is 13.8. The sample standard deviation is 3.5, and the sample size is 50. Okay, so we got those for free. Now, you may see in a situation, for example, in the homework that's associated with this case study, I don't give you these summary statistics straight up. You have to compute them from the sample. And given that the sample size is so large in that homework, you will want to use Excel to compute x bar and s. All right, but we get these three values for this example. And then we need the z-value. It's 2.575. Where does that come from? Well, it comes from the confidence level. The confidence level is 0.99 because we got a 99% confidence interval. So alpha is 0.01. And so z sub alpha over 2 is z sub 0.01 over 2. All right, so that's z with the subscript of 0.005. And if you look in table N, you'll get that z-value is 2.575. Basically, you're looking for the z-score that has a right area of 0.99. I'm sorry, that has a left area. You're looking for the z-score that has a left area of 0.995. So we got our 4 pieces in here. Plug them in. Start simplifying. Simplify the standard error of x bar. That's roughly 0.50. Multiply that times 2.575. You get 1.29. And add and subtract 1.29, also called the margin of error, to our point estimate, and you get these values in here, 2.51 up to 15.09. So interpreting this, we're 99% confident that the average amount of gas pumped for all sales at Nails is between 12.51 and 15.09 gallons. So if somebody said, I think that the amount pumped is around 14.5 gallons, this confidence interval wouldn't be strong evidence for that, but we would say, hey, that's a plausible value. 14.5 gallons is a plausible value based on the data. On the other hand, if somebody said, well, I think the average amount of gas pumped is at 18 gallons, we would have strong evidence against that sort of claim. We think, well, no, the data suggests that the average is between these two values here, and 18 is not in that range. Okay, so that's the interpretation. That's the example for Nail and his gas station. Okay, a hypothesis test and confidence interval there. Okay, now moving on here to the last part of the notes in chapter or in case study 2b. Notice it didn't take us that long to go through case study 2b. Very similar to case study 2a, except our test statistic. We had to develop the central limit theorem and its ideas to talk about the test statistic. But here is a chart, and we have seen this chart or parts of this chart before. This is an important chart. It summarizes what we've done in terms of statistical inference so far in this class. So far in this class, and we've filled out these first 2 rows in previous lectures. For case 1a and case 1b, we were doing inference on a population proportion P. Remember that? And in case 1a, we had a small sample size of binomial data. Case 1b, we had a large sample size of binomial data. Now, this being small and this being large, that changed the test statistic and distribution we used the null distribution we used to perform a hypothesis test. So go back and look at your notes. Case 1a, the test statistic here is the number of successes out of our sample, and it follows a binomial distribution. And the test statistic here is the number of successes out of our sample, or that number standardized, and that follows a normal distribution. And then we had a confidence interval formula for that. P hat plus or minus z times root p hat times 1 minus p hat over n. Anyway, so I'm not going to write that down. You can go back and look at your notes for those expressions. Just to show you the similarities of what we just did in case 2b with case 2a, I did write down the case 2a information. In both case studies, we were interested in doing inference on a population mean mu. Now in case 2a, we had a random sample of normal data. This was the pulse wave velocity data. And we used this test statistic to do a hypothesis test. That test statistic followed a t-distribution. This was called a t-test. If we have a random sample from a normal population, we're doing what's called a t-test. The corresponding confidence interval here is a t interval, x bar plus or minus t sub alpha over 2 times s over root n. That's case 2a. This will work for any size data set as long as the data comes from a normal population. Now, for case 2b, we also did inference on mu. We had a large data set, but our sample in case 2b did not appear to come from a normal population. It appeared to come from a left-skewed population. But the CLT came to save the day. It said, hey, this ratio here, if n is large, notice it's the same as that one. The ratios are the same. But if n is large, this ratio follows an approximate standard normal distribution. The central limit theorem gave us that result. Not because we sampled from a normal population, but because we had a large sample. This follows a normal or approximate normal distribution. The corresponding confidence interval here is x bar plus or minus z alpha over 2 times s over root n. And you see the similarities between case 2a and case 2b. The test statistic is they're the same. If you wanted to put a t in front of this and a z equals in front of this, that would be fine. But the respective null distributions and confidence intervals are different. It all depends on the conditions in the problem. Do we have a normal population? If we do, then go with the t-interval and the t-test. If we don't, but we also have a large data set, if we don't have a normal population, but we do have a large data set, then we can apply the central limit theorem to the distribution of this statistic and also in turn use this confidence interval for the population parameter mu. All right, I hope this was helpful. Recall that we have a homework set that is due, that one that was due on Monday, the 7th, one that is due on the 9th, and of course our exam is coming up on the 14th of November. Those are all those were announced in previous classes. All right, I hope this has been helpful. If you have any questions, feel free to email me or contact me during office hours. Thank you.